Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting our third lecture for the week number 6 for the course of wireless and mobile communication. In our previous lectures, we talked about two important phenomena, mainly reflection and diffraction. And we also discuss how these two phenomena they affect the propagation of electromagnetic wave or wireless signals when they propagate through the open environment. We also discussed path loss modeling and calculation of diffraction loss based on these phenomena. Now let us continue our discussion on this path loss modeling and include another important aspect, which is the third phenomena related to propagation of electromagnetic field, and that phenomena is called scattering. Scattering is actually the phenomena which refers to dispersion of the wave in different directions. Whenever the wave hits some irregular object, for example, it's illustrated in this diagram here. A ray goes to this tree, and when it emerges in out of tree, because the tree leaves they cause an irregular reflection, so this ray is scattered in variety of different direction. You can see that this ray is going towards different sides. So this diffraction actually, this scattering is actually a phenomena where the wave gets scattered because of the objects which are small as compared to the wavelength of the wave. Generally, this scattering is caused by rough surfaces or small irregular objects and similar stuff when the wave propagates through the environment. And an important aspect of scattering is that in some cases we get the received signal which is stronger than what is predicted by reflection and diffraction models alone. So because of the scattering, because when the ray gets scattered, so even the ray which is not going towards the receiver, after scattering, a component of that ray might be received at the receiver side. So the scattering sometimes increase the overall received power because of the random scattering because of the small objects. Practically, it's very it's close to impossible to incorporate the effect of scattering, because scattering can occur from variety of different objects, and there is no regular phenomena which can be included for the calculation of scattering. One simple model in that case is known as log distance path loss modeling. A log distance path loss modeling is kind of a generalized model related to the models that we have previously discussed, like free space and two-ray reflection model. If you recall the free space path loss model or two-ray ground reflection model, in that model we discussed that the received power is actually dependent on the distance. So if we increase the distance, the received power gets reduced. In other words, there is a relationship between this received power and the distance, and that relationship is represented in form of a specific power. For two-ray ground reflection power, we saw that this power in this relationship was n is equal to 4, and for free space path loss modeling, if you recall, we saw that this path loss index was n is equal to 2. So this n is actually an important parameter that actually determines how much the power is degrading or reducing when we increase the distance. This n is known as path loss exponent, or in some cases it's known as path loss index. Generally, this the path loss index n, it depends on the specific type of propagation environment. For example, for free space, we have discussed that this path loss index is 2, but when we go for other components of wave, that like ground deflection model, in that case the path loss index gets increased, and we take that path loss index n is equal to 4 when we discuss the ground deflection model. This d naught, which is represented here, is actually reference distance, which we have previously discussed as well for both free space as well as the two-ray ground deflection model. So this d naught is a reference distance, but as we know that it should be chosen in such a way that it exists in the far field region of the transmitter. So typical value of d naught that we commonly use is 1 kilometer when we are talking about large cellular coverage, and when we are talking about for smaller cellular coverage like microcellular systems, in that case d naught is of the order of meters. For example, 100 meters is commonly used, but if we are using even smaller cells, in that case we may use d naught to be equal to 10 meters. So a more generalized model, which actually generalizes the free space path loss model as well as the two-ray ground deflection model, is this log distance path loss model, where we have a generalized parameter n, which can be calculated to find the specific behavior of an environment. And we will discuss an example as well in today's lecture, how we can calculate n from the measurements. So in general, if P naught is the power at the reference distance d naught, in that case the received power at a distance d is given by this formula. There is a mistake here. It should be written as log distance path loss modeling. I will correct it in the final version. So PRD is equal to P naught d naught multiplied by d naught upon d raised to power n. We can also represent this equation in terms of decibels. So if we are using dBm unit, in that case P naught should be taken as dBm, and for d naught upon d we have to take log and multiplied by 10, and you can see that this power n becomes this product because of the presence of logarithm here. An alternate expression for the same case is with respect to the path loss instead of received power. You can see that the above expression is actually related to received power. If we represent the same thing in terms of path loss, so path loss is actually, because path loss has the reverse behavior of received power. When the path loss is increased, the received power would get decreased. So path loss is actually proportional to the d upon d naught raised to power n. So if we represent this thing in decibels, in that case path loss in decibels would be whatever path loss we have at the reference distance d naught, of course in decibels, multiply plus this dB value of d over d naught raised to power n. So 10n log d over d naught. So this is the expression that we can use if we are calculating the path loss in decibels. These are the path loss for some commonly used environments. Actually most of these path loss has been calculated on the basis of different types of measurements. So for example, for free space we have previously calculated that path loss index is 2. If we are using an urban area cellular system, in that case path loss ranges from 2.7 to 3.5. For shadowed urban cellular region, the path loss is around 3 to 5 value. for an in-building communication, provided there is a line of sight component available, the path loss is significantly small, which is of the range of 1.6 to 1.8. If there are obstructions in the building, in that case path loss goes between 4 to 6. And if we are working in a factories, an indoor environment which has some obstructions as well, in that case path loss comes out to be 2 to 3. So by using this different value of n, we can easily model different types of environment by using the log distance path loss model which I showed earlier. So far we have discussed about the path loss and the received power or path loss modeling for the signal. The next important thing is shadowing. What does shadowing represent? If you recall, the path loss is given by this expression PLDB is equal to PL d naught upon d 10n d naught plus 10n log d over d naught. If you have a fixed value of d, in that case you can estimate the value of PL. But practically this does not happen. What happens is that there are variations in the received power, even if the d naught is constant. For example, if you take 100 measurements at d naught, say for example 1000 meters or 1 kilometer, if we are taking 100 measurements, in that case all those measurements would not have same value. They will be different with certain value. So there are differences even if we are working at the same distance. So this path loss, actually it does not truly represent the exact value of the received power, because there is some sort of randomness in the received power. That randomness is caused because of cluttering, because at different regions there are different cluttering effect, different types of buildings and vehicles are around, and that difference in effect causes differences in the received power. Generally the received power has follow the Gaussian distribution, and because we are using this path loss or the received power in decibel units, in that case this shadowing should also have the decibel units. So in decibel units, this variation, random variations, they follow the Gaussian distribution. In order to mathematically model that, we represent that effect by a random variable, or we call it a shadowing random variable. This random variable, random effect of shadowing, is actually represented by this x sigma random variable. This x sigma, as I mentioned, that this is actually following Gaussian distribution. So in that case the path loss would have this value, which is actually the first part is the deterministic part. This is the deterministic part, and plus this x sigma, which is actually representing the randomness occurring because of the shadowing. So this is an illustration of Gaussian distribution, this Gaussian random variable, which is representing shadowing. It has a zero mean, so mean value is 0, but it has some standard deviation here. Actually standard deviation would be there. If variation is strong, the standard deviation will be high. If the variation is small, the standard deviation will be low. So these the addition of this random variable x sigma takes into account the received signal variation because of the shadowing, and this phenomena is easily observable from the measurements as well. As I would show in the next figure, you can see that this figure represents the number of measurements that were taken place at different distances. So at x-axis we have TR separation, at y-axis is the received power. So if you see that, for example, if I take the distance to be equal to 3 meter, like 0.3 meter, which is here, you can see that these all are the received powers at that particular distance. So at one distance you see that is a range of powers that are received at this distance. Similarly, for all other distances you can see that a range of values are received. These straight lines, they are representing the curve, which are representing different values of n. This one is n is equal to 5 curve, this is for n is equal to 4, this one is for n is equal to 3, this one is for n is equal to 2, and this one is for n is equal to 1. So you can see that for each curve these values, they have some deviation around this mean value. So if for all our radiations, for all the measurements that occur in this, that are represented in this figure, if we calculate the overall value of the path loss index, we see that the path loss index comes out to be n is equal to 2.7, which is illustrated by this thick line here. You can see this thick line is here, which is actually around at the center of all the measurements. So basically this thick line is representing the mean value, whereas we have some deviations around those values which are actually caused because of the shadowing effect, and this standard deviation of that random variable comes out to be 11.8 decibels. So in order to truly represent the path loss model, in addition to that log distance path loss model, we also use this log normal shadowing, which represents the random variation that occur around any specific value. A good thing is that if we have measurement results, we can easily calculate the values of n and sigma. As I mentioned that in today's lecture, we'll take an example how to calculate this n and sigma if we know if we have the measured values at different distances. So a more generalized model that we have discussed is log distance path loss model. The only difference that we see from free space and the two-ray ground deflection model is that it's actually more generalized in the sense that it has a more general value of n, and n can different values of n can be used to represent different environments, as illustrated in this table here. So let us take a problem that I was talking about, that we can calculate the value of path loss index as well as the random variation, this standard deviation of variation, if we have some measurement results. So we have 4 received power measurements which are illustrated here. So at 100 meter distance we have 0 dBm received power, at 200 meter we have minus 20 dBm received power, at 1000 meter distance we have minus 35 dBm received power, and at 3000 meters we have minus 70 dBm received power. So these measurements are taken at different distances, and all distances we get different powers. So if we are trying to model our system as the log distance model, which we have discussed in today's lecture, and which is also represented by the equation here, plus there will be some randomness which is representing the shadowing effect. As we know that in modeling the system we generally take up a reference distance d naught, and for this problem we are taking d naught to be equal to 100 meter. So basically this first value is actually representing our the reference value where we are using measurement at the reference point. So first part is to find the value of path loss exponent. Although there can be variety of different techniques to calculate path loss exponent, one of the most common technique is minimum mean square error method. So we calculate the path loss index in such a way that the total mean square error is minimized. The second part, B part, is actually related to the calculation of standard deviation that we'll discuss later, and third part is related to using this formula to calculate the received power at a specific distance of d is equal to 2 km, for which we have no measurement here. You can see that we do not have measurement for d is equal to 2 km, but once we establish the parameters for this model, we can also calculate the received power at d is equal to 2 kilometers. So let us start the first problem, which is calculating the path loss index n. So you can how can we calculate the path loss index? The criteria that we are using is minimum mean square error. What is mean square error? Actually, we try to model in such a way that the difference between the measured value and the model value. The model is represented by this equation here, and measured values are represented here. So the difference is minimized in the sense that whenever we calculate the mean square error or mean square distance, and that value is minimized. So actually what we are doing, we are trying to minimize the sum of square errors or mean square error. Actually, sum of square error is not exactly the mean square error. For mean square, you have to divide by total number of values, which is 4 here, but it does not make any difference for calculation of mean, for calculation of n, whether you divide it by 4 or not. So we calculate the sum of square errors. So there are 2 powers at each distance. Which 2 powers? First one is the power that we get from the measured value. So this is first power, and second would be the power which is represented by this formula here. So there are 2 different types of powers. So I have indicated the measured power as Pi, and the power which is coming from this formula, the path loss formula or received power formula, because we are given the received power, not the path loss. In that case, we need to use this received power formula instead of path loss formula, but both formula, they are same. So this Pi hat is actually representing the power which is calculated from this formula. Because we are calculating at 4 different distances, so we have to calculate the power at 4 different distances. So we have P1 hat, P2 hat, P3 hat, and P4 hat. P1 hat is the first distance value. So the first distance is 100 meters. So we know that we are using the reference d naught to be equal to 100 meter. So P naught dBm is taken as 100 is 0, because this is our reference value. So at first value P1, 100 divided by 100 is log 1, and log 1 is equal to 0, so it comes out to be 0. For second distance, which is 200 meter, if we use the same formula, so again this P naught dBm comes out to be 0, because this is our reference value. And if we replace d naught by 100 and d by 200 here, in that case we get P2 to be equal to minus 3n. Similarly, P3 hat corresponds to the value that you have at third distance, which is 1000 meters, which is so at 1000 meters this d becomes 1000. So this d is actually 1000 here, and P naught dBm is again 0, because this is our reference value, and if we simplify this, we get it to be minus 10n. Similarly, for P4n, we will use 4th distance, which is 3000 meters. So for 3000 meters, this d comes out to be 3000, and again P naught dBm is 0, so we get minus 14.77 n. So you can see that we have all 4 values which are calculated from the standard formula, log distance path loss model formula. So all these values, they are calculated from the formula, and we are already given the measured values here. which are represented in this table here. So we can use these two values to find this Jn, or which is representing the overall sum square, sum of the squared errors. So if we simplify this, you can see that this Jn would be actually comprising of 4 terms, because we have 4 measurements. The first term is the difference between the first measured value, which is 0 dBm, and this formula value, which is 0. So first term is 0 minus 0 squared. Second term is difference between the second measured value. The second distance is 200 meter. The measured received power is minus 20, and the formula received power is minus 3n. So second difference is minus 20 minus of minus 3n. Similarly, third value would be the difference between third measured value. The measured value is minus 35 dBm, and the formula value is minus 10 only. So if you substitute here, so this will be minus 35 minus of minus 10n whole squared. Similarly, the fourth difference is between fourth values, which is minus 70, and the formula value is minus 14.77n. So fourth value will be minus 70 minus of minus 14.77n whole squared. So you can see that these are simple whole squared formula, and you can simply expand them, and this Jn turns out to be this value, 65.6525 minus 2887.8 n plus 327.153 n square. You can see that this function, which is sometimes called objective function, or in such type of problems, this function is actually dependent on n, and we want to find the value of n which actually minimizes this Jn, because the criteria that we are using is minimum mean square error. So this function is actually representing the square error, sum of square errors, and we want to minimize this thing. So in order to minimize that, we differentiate this function with respect to n here, and if you differentiate, you can see that the first term would become 0. For second term, n, the derivative of n would be 1, and for third term, the derivative of n square will be 2n. So you will see that you will be getting this value 654.306n. And in order to minimize this thing, we have to equate it to 0. So if we equate to 0, you can see that, just focus on this part, you can see that this is a simple equation which is dependent on n, and we can simplify this equation to get the value of n. If we simplify this thing, you can see that n would be 287.8 divided by 654.304, and this comes out to be 4.4. So these measured values, they actually correspond to the path loss index of n is equal to 4.4, sorry. So this completes our first calculation. How can we calculate the path loss index if we are given the measured values? Now let us move on to the second part. We want to calculate the standard deviation. In general, we know that from statistics, standard deviation is actually square root of variance, and variance has very simple formula. So rather than calculating standard deviation, we start with calculating the variance, and then we will take square root to calculate the standard deviation. So let us start with calculating the variance. Variance is actually represented by sigma square. Variance, when we calculate the variance, if you recall, the variance is x minus x bar whole squared summation divided by the whole number of values n. So we are using the same formula here. The x here is actually this received powers here. The mean value are represented by this path loss formula values, because as we discussed, for path loss, the calculated path loss is actually represents the mean of those measured values. So these pi values that we have previously calculated here through the formula, they are actually representing the mean values of the path loss. The mean values of the received power calculated from the path loss formula. So we can use this relationship. Again, we have to calculate the difference between this measured value and the value which comes from the formula. And again, because we have 4 different measurements, so there will be total 4 terms here, and we have to divide it by 1 by 4 in order to calculate the variance. So this will be, the first term is 0 minus 0. If you refer back here, you can see that the formula value is 0, and similarly the measured value is also 0. For second term, the measured value is minus 20 and formula value is minus 3n, and the same is represented here. The difference is minus 20 minus of minus 3n whole squared. Similarly, we have calculated the difference of square for the third value, which is minus 35 minus of minus 10n, and similarly we have calculated this value. And from the previous expression, previous part, which is the part A, we have already calculated the value of n, which was 4.4. We can simply substitute the value of n, which is 4.4, in all these places here in this expression, and you can see that if you substitute the value of n is equal to 4.4, all these terms would become numeric values, and you can simplify those numeric values, and it turns out that after simplifying this expression, this variance comes out to be 38.09. But in the problem, we were asked to calculate the value of standard deviation, and that standard deviation should be calculated by taking square root of the variance. So if we take square root of 38.09, so we get the value of 6.17. And again, I must remind you that this shadowing standard deviation is also in decibels. So because we are calculating all the powers in decibel, so this standard deviation also comes out to be in decibels. This 6.17 decibel of standard deviation is relatively large. Actually, it's a large number. Generally, if we have well-defined measurement setup and a uniform type of environment, if there is not much difference in the environment, the standard deviation is relatively small. But for this particular problem, we are getting relatively large value of standard deviation because we did our calculation on the basis of very few number of measurements. We only took 4 measurements in account. Practically, we take a lot more measurement. For example, if you go back to the figure that I illustrated, and you can see that this entire dots, each dot is actually representing one type of measurement. So these entire dots, they show that there are like hundreds or thousands of measurements that were taken in order to make a useful in order to conclude a useful result. So generally we need to have lots of measurement, and if we have better measurement and we do not have significant changes in the environment, in that case this standard deviation is kind of reduced. Okay, so let us now move on to the third part, which is actually calculating the received power at a distance of 2 kilometers. So we want to calculate the received power at a distance of 2 kilometers, and you know that we are already given received power at the reference distance. Our reference distance d naught is 100 meters, and we are already given that the power at the reference distance is only 0 dBm. So we can use this value to calculate the received power at d is equal to 2 kilometers by using this received power formula, this log distance formula, which I have shown earlier in today's lecture. The same formula can be used. This P0 dBm is already given to be 100 dBm, N we have already calculated, D naught is 100 and D is 2 kilometers as mentioned in the problem. So let us move on to our C part. So for C part we can use this log distance formula, and if we substitute this value, PR, we are calculating PR to be 100 meters, PR at 100 meter which is 0 dBm, and path loss index is 4.4, and this entire log 100 upon 2 kilometers which is 2000 meters. So in that case the received power is given to be minus 57.24 dBm. So this is the received power which we have calculated using the path loss formula or received power formula based on the log distance model. You can see that this is actually a constant value which is actually representing the mean value of the power which is received at 2 kilometer. Actual values will be different. How much different would be there? Which we have already calculated, that difference would be a Gaussian random variable with a standard deviation of 6.17 dB, which we calculated in the part B. So the shadowing effect in this received power will be modeled by a Gaussian random variable. So if we want to include that shading effect as well, so we have to add a random variable here, x sigma, where sigma is this 6.17 dBm. So if we add this thing, so this will show that there will be some randomness which is actually modeled by that shadowing effect. So this was our problem, and in this problem I tried to explain that how can we calculate the path loss index for this log distance model if we have some measurement values, and this is a very common technique used to model the path loss index or path loss calculate the path loss index values for different types of environment. So practically when we are calculating this received power, which is sometimes known as link budgeting. So link budgeting is generally done using analytical formula like we have done from for free space path loss modeling or two-ray ground deflection modeling, or sometimes we do this link budgeting on the basis of empirical models, like we have discussed in the previous example, that if we have certain types of measurement scheme and if we have certain measurement results, in that case we can use curve fitting techniques or analytical expression to model the overall behavior of the environment. Generally for this empirical approach we need to make lots of measurements, like hundreds of measurements are required to accurately model an environment. The good thing about this empirical modeling is that all the propagation factors, they are included because we are working on the actual measurement. So no matter how many different propagation factors are there, they are already included in those measurements. But the disadvantage is that the model would be valid only for the environment for which you have done the measurement. For other types of environments you would be required to do new measurements. So that empirical model would be valid only for limited type of environment for which you have conducted the measurements. So this is our discussion regarding the log distance path loss modeling and how we can calculate the path loss index from the measured values and what are the approaches that can be used to model an environment to calculate a specific path loss index for that environment. So we stop our discussion here. Inshallah we will start some more we will discuss some more models in our next week's discussion, inshallah. Thank you all.